All right, so in the second video here, kind of topic 12, we first talked about spontaneity. In the first video here, we're going to talk about entropy. Okay, right. So this thing that also determines spontaneity is related with what is called entropy. Okay, and entropy, right, is not something as like straightforward to think about as internal energy, right? Potential energy, kinetic energy, right? We've been talking about those things for a very long time in school, right? Back to high school and things of that nature, right? But entropy, okay? Entropy is related with kind of the dispersal of matter and energy, okay? Basically, entropy is this thermodynamic quantity that quantifies the fact that things mix, things, you can think of things want to mix, things want to get randomized and disordered, right? It's not necessarily that there's some sort of desire for this chaos, right? It's more kind of, it can be related back to statistics, and this entropy is very related to statistical thermodynamics and things like that, right? And the idea, right, so in this example here, right, I have a container, right? Think of our gas separated into two chambers, right? I have, all the gas particles on the left side of the container right here, right? These are different scenarios, 1, 2, 3, 4, 5, right? In scenario 1, right, all my gas particles on the left side. Scenario 2, all of them are on the right side, okay? Right? Scenario 5, right? Scenario 2 and 4, right, kind of have 3 and 1, and scenario 3 has 2 particles mixed in the middle, right? Right, and see, those are all the different possible ways I can arrange these particles, right? And so, right, for having 4 particles, okay, total, right, 1 out of 5 scenarios has all the particles on the left, right, and another 1 out of 5 has it on the right. So you can think of it as like 2 out of 5 of these scenarios have like an empty chamber, right? Well, 3 out of 5 don't, okay? That's for 4 particles, okay? So 2/5 of the time, you can have an empty chamber, right? Now, that's relatively likely to happen. But if now I have 100 particles, right, it would be something. I have no idea actually what that comes off to in the top of my head, but let's pretend, right, it will be something like 2 out of 100, right, for 100 particles, or 2 out of 10,000 for 10,000 particles, right, and things like that, right? So right, then to get all of the particles on one side, right, probability of that happening is drastically decreases as the number of particles increases, okay? And this is ignoring the fact that, when arranging these particles, right, say for case 3 here, right, if I labeled these particles 3, 4, right, there's a bunch of different ways I can put 2 particles here, 2 particles here, if these particles are labeled, right? If they're not labeled, it's just, they're all identical, but if I think of them being labeled, there's a bunch of different ways that this can occur, right? I can have 1, 2, 3, 4, I have 1, 3, 2, 4, 1, 4, 2, 3, right? 2, 3, 1, right? So you see my point, right? You have a bunch of different ways of doing that, okay? But for example, everything being on the left, right, there's just one way of doing everything on the left, right? So again, the number of ways, right, that number 3 here can occur is significantly greater than the number of ways that 1 or 5, say, can occur, okay? And so an entropy is related with kind of the count of these ways, right? So the thermodynamic definition, well, we'll get to kind of the thermodynamic definition of entropy, but the statistical thermodynamic definition of entropy is related with the natural log of this capital omega here, this kind of weight function, this partition function for your system, and this is right. This capital omega is just a statistical thing, essentially, right? It's essentially related with the count of number of ways you can arrange your particles in a certain way, okay? So in this top way, I can arrange my particle one way here, okay? In this chamber here, I can arrange, if I label my particles, again, 1, 2, 3, 4, okay? I can arrange my particles in 4 different ways, okay? In this chamber, I have, let's see here, 1, 2, 3, 4, 5, 6 different ways, and 4, right? That chamber and so on, right? So the number of ways that I can arrange my particles, right, varies, right, depending on how they're situated in there, right? And again, this evenly mixed is the most likely to occur, okay? And that's what entropy is sort of a measure of, is sort of what is the most likely thing to occur statistically, right, through probability and things of that nature, right? And that has some weight in terms of whether or not something's going to happen, right? Right. So again, a simpler example, this is 2 particles, right? I have, you know, one way of doing this, one way of doing this, and I have 2 ways of doing this where I mix them evenly, right? So again, it's more likely that they're evenly mixed than that they're separated, or that they're both on one side of my container, okay? Right? This works as well with energy, okay? Right, we talked about the 0th law of thermodynamics, right? That temperature, right? 2 things in thermal contact will reach the same temperature, right? And that energy flows from high temperature to low temperature. It's the same kind of concept, right? You think of temperature as a form of matter, right? In which you have high density and low density on one side and the other, right? Particles will flow from the high density region to the low density region until there's equal density on both sides, right? Because then things are equally mixed. And the same thing with energy, right? Energy is, you know, can be transferred, right? Kinetic and otherwise. And so, you know, if I have something at a high temperature, something at a low temperature, that energy will get transferred from the high to the low temperature, right? You can think of, you know, a high temperature object is something that's moving very quickly, right? And a low temperature object is something that's moving very slowly, right? Well, like when I put these things in contact with each other, right, what's going to happen is that high temperature object is going to hit the low temperature object, right? The high velocity object is going to hit the low velocity object and transfer some of its momentum to the lower velocity object, which is going to speed the lower velocity object up and slow the higher velocity object down, right? And again, this temperature is a measure of like average thermal kinetic energy, okay? And so when doing this, right, this transfer of velocity, right, is effectively a transfer of temperature, right? And so, right, again, when things get brought into thermal contact, right, you know, this need to go from high temperature to low temperature, right, until you reach equal temperature is related with entropy, right? So with this dispersion of energy as well as matter throughout your system, okay? Right, in crystal systems, right, there's higher entropy systems when there are things that are more disordered, right? Because again, if everything's perfectly ordered, there's like one way I can do this, okay? Well, if things are disordered, right, I can rotate some of these different particles, right, and all of a sudden it's going to make a new looking crystal, right? And this new looking crystal, right, is different from the other one, right? So there's a bunch of different ways I can create these disordered crystals, right? And so I'm going to have much more entropy for a disordered crystal than an ordered system. Because there's more ways that I can generate this thing, there's more ways I can create a disordered system. Yeah. In vibrations, right? The more vibrational modes your molecule has, right? The more degrees of freedom it has, the more entropy that thing has, right? Because right, if there's more vibrational modes, more things are moving around in all sorts of different ways, right? So you got this energy spread out, doing all sorts of different motions and things like that in your molecule, right? And that's causing it to have greater entropy. Okay. You know, part of the reason why things dissolve in solution, right, is because you're mixing things together. When you mix things together, you create a lot more disorder, a lot of variety of arrangements of things, right, and it increases the entropy of that system, right, and so again, The entropy is this measured disorder, right, of both matter and energy. Okay. So, right, if we think of entropy of phases, right, the entropy of a gas phase is significantly greater than that of a liquid, which is greater than that of a solid, right? Because the gas phase, you got things completely independent of each other, bouncing around, moving around, right? Huge amount of entropy, okay? In the liquid, things are able to rearrange from each other, but they're still kind of packed together in some slight organized way, right? And then solid, things are very well organized, well placed, so there's very low entropy, okay? When thinking of chemical reactions, right, that means that basically the entropy change of the chemical reaction is going to effectively be determined by which side has more gas particles, okay? Right? If you have more gas particles on the product side, that's going to have a positive change in entropy for the reaction. If you have more gas particles on the reaction side, that will have a negative change in entropy of that reaction. Okay? And again, things at higher temperature have higher entropy, right? More energy, more things that can move around, and more disorder that can be occurring in your system, right? Right.